So we are going to prove that the dual space of X is a Banach space. So so what we need to do for the proof, so we consider a sequence ln of linear functionals, so of elements of the dual, and we want to show that in fact this sequence ln converges to a linear functional, a bounded linear functional L on X. So since ln is Cauchy, this inequality holds. I have some people. So this inequality holds. So for all epsilon, if n and m is large enough, then the norm of ln minus lm is less than epsilon. So the norm here is the norm that we defined previously, the dual norm. All right. So specifically, this means what? This means that here, for all x in the space X, this thing is valid. So it's not a double bar here, because ln of x belongs to is a scalar. So it's a scalar. So it should be a single. There's a typo here. It should be only one bar. Okay, but by definition of the dual norm, this inequality holds for all x. Well, so this is the key point. This is the key point, because now, in fact, what that gives me is that now I have a sequence, a Cauchy sequence in the scalar space. And the scalar space is either R or C, so that and C or R are complete. So every Cauchy sequence in R or C converges. So from this inequality, I know that there exists some L of x such that for fixed x, ln of x converges to a L of x. All right. So now, since ln is linear, if I take the limit, the limit will be also L of x will be also linear. So, but we need to prove that the functional that we obtain is bounded. Okay, but we know that ln is Cauchy in the. We know that ln is of Cauchy. It's our first assumption. And for a norm, I have always this inequality. So if you don't know this inequality, it holds for you can do it on in R. It holds for every distance. So so I'll let you figure this out. This inequality holds. So here now a bar is missing too, right? A bar is missing here. And so from this inequality, what do I deduce? I deduce that the sequence norm of ln is also Cauchy. Yeah. So I deduce that now ln is a Cauchy. And since it's Cauchy, you know that every Cauchy sequence is bounded. It's a nice exercise to do that. It's a topology exercise, and so now the norm f ln defines a sequence which is bounded. And so since, all right, now I have this inequality because so ln is we know that ln is a bounded linear function also. So this holds. Okay, so the first part here, this comes from the fact that ln, for each n, ln is a bounded linear functional. And so by definition of the norm, the dual norm, this inequality holds. And then this comes from the fact that we just said that the norm of ln is bounded. So there exists a constant c such that norm of ln is less than c. Okay, but now I obtain that for each x there exists a constant. This constant is not dependent on n. It not depends because c is a bound for the norm of ln for all n. So now I got that ln of x is less than c of x, c of norm of x for all n. Okay, and so for each x, ln of x converges to L of x, so I can take the limit and I obtain that, which means that my linear functional is in fact bounded. So it remains to prove that that in fact ln converges to L in the for the dual norm. But this comes so now since I have this, I can take the limit again for with one of the indexes, and I get that, and this means that for all epsilon, the norm of ln minus L is less than epsilon, which means that in fact it's true. Lm converges or ln converges to L when m goes to infinity. So next I propose here a small exercise. So this exercise, which relies on an application of the Banach theorem, proves that you can always define the dual space of a Banach space, and it goes like that. So if you have so you consider n linearly independent vectors in a normed space X, and assume that you have also n scalars, then there exists a bounded linear functional L such that L of yj equals alpha j for all j. But the point is that L is defined on the whole space X. All right, because okay, so try to. The solution is quite natural. So try to come up with the solution. All right. So how are we going to proceed with that? So first, we are going to define the functional L, right? So its definition is given by the constraint that I have, right? So I need to have L of yi equals alpha I. So, well, so let's call capital Y the span of the given vectors y1 till yn. So if I, so I must have L of y equals alpha I. So this defines, since L needs also to be linear, this defines L on all y, because so let's y belongs to capital Y with y equals sum from y equals 1 to n of, for example, beta I yi. Then L of y equals sum of y from I from 1 to n of beta I. This is bilinearly Lyi, which is alpha I. So by this way, I define L on the whole space Y. So L is linear on Y, right? Can you do that? Can you prove that L is linear on Y? So let's do it. For example, let's y1 and y2 in Y. I'm looking at L of y1 plus y2. This is by, because I will write it on the basis. So this will be written like that. So sorry. Here. So this will be, sorry. So the high is here. Those are my y. And here I will have another set of scalars by1 plus, so this is for y1, this is y1, and y2 equals the sum of y, and here I have beta 2I. Okay, but then what? Then I can put the y in front. So this is sum over I of beta I1 plus beta I2 yi. And so now I can because L is linear, I can take this out. So finally, so L of yi, but this is alpha I. And finally, I get L of y1 plus L of y2. Okay, so in the same way, you can prove that L of lambda y equals lambda L of y for all y in y. Okay, so L is linear. Is L bounded? Is L bounded? So if I want to prove that L is bounded, so again I have Ly. L is bounded on the space capital Y. Is it bounded? So I will have L. So this is, we know, this is that. So I deduce that if I take the norm of Ly in R or C, this is less than sum of y equals 1 to n of beta I, alpha I. And so this is less than the max over I of alpha I times sum of beta I. So now here's the point. This is a norm on Y. You know, this is a norm 1. So this is a norm on Y, but when I deal with finite spaces, all the norms are equivalent. So there exists some constant C such that, so this first term, I don't touch it, but then a constant C times the norm of the Banach space. All right, so this is because all the norms are equivalent on finite spaces, finite dimensional spaces. Okay, so what I get, so L is bounded. All right, so L is bounded. So L is bounded. And so now I can apply some of the results that I previously that we did in chapter 1. So it's based on the Banach space, but from the Banach space we had a corollary for real, for bounded linear functionals, and a corollary for also bounded linear functionals on C. So from that now, so from results in chapter 1 in section 1, so we deduce that L can be extended to a bounded linear functional on X. So this is from the Banach theorem, basically. Okay, so in fact, we already proved the first part. What we didn't prove is that the norm of L in X prime equals the normal L on Y prime. Well, so let's go through the proof. So I will start with the remark of the students here. That was that in fact, yes, since L is in this space, he belongs to the dual of Y, you have that L of X is less than norm of L in Y prime times norm of X but here for all x in y. Okay. Look, again, what I do, I did it a couple of times just before, but let's remind some more details. So I apply the Banach theorem and its derivatives, I should say. So with the idea is to take P of x equals norm of L in y prime times x. Then I apply the Banach theorem or its corollary of the proposition which is following for the context number C. And so what tells Banach theorem is that I have next, so I obtain, what do I obtain? I obtain that P can be extended to the whole X. So L can be extended to the whole set X with L of X less than, this is the same constant, that's important. So difference here, the difference here is what? Now it's for all x in x, that's the difference. Okay, and so that's good. Why? Because now I have that for all x this inequality holds. So if I take the sup here, I obtain, so taking the sup gives that norm of L in x prime is less than L in y prime. And this was the hard part, because on the other hand, by definition, I have that the sup of x belongs to y of L of x divided by norm of x is less than the sup of x belongs to x of L of x divided by norm of x, because x is a greater set, y is included in x. So if I take the supremum, the supremum on a bigger set is bigger. I can choose with more elements. So this gives that norm of L in y prime is less than norm of L on x prime. So combining these two gives norm of L of x prime equals norm of L in y prime. Okay, so next we are going to prove this proposition. So for all x node in X, I can find a bounded linear functional such that the norm of the linear functional is equal to the norm of X node. And furthermore, this equality here holds when apply the linear functional to X node. So in fact, again, with these two informations, I have not so much room to other things. So what we are going to do is all right. So first, we're going to again. It's an application of the Banach theorem, because so we are going to work now on so the span of X node, which is alpha X node with alpha in K. All right. So now I'm going to define on Y. I'm going to define phi of X node of lambda X node equals lambda times the norm of X node square. So first it has to be a linear functional, and two, it has to verify that. So I have no such a choice. Okay. All right. So now I can apply the Banach theorem, but for first, what I have is that so if I look at now the norm of phi node of lambda X node, by definition, this is lambda and yeah, so this is lambda X square. So if I look at, so sorry, here there's a detail that's not right. This is there. Now, if I look at the quantity again, if I look at this quantity, this is exactly, so if I take here, so this implies that the norm of phi X node on what on Y is equal to X node. And from the previous proposition, so my phi node can be extended to a linear functional on X, and I have that phi X node on X prime equals phi X node on Y prime equals X node. Okay, and yeah, and the other point is I got it by, sorry, by definition. If I replace lambda by 1, I got the other one. Here it's here. This implies that phi of X node equals X0 square. I take that with lambda equals 1. That's it. So finally, the following proposition holds. So for all X, we have that the norm of X, so X is a Banach space. It's endowed with a norm, and if I take the norm of X, it's equal to the supremum of all the phi in X prime such that the norm of phi in X prime is less than 1, and I take the supremum over all this phi for this fixed X, and I take the absolute value, and this is the norm of X. So this is our proposition that we are going to deal with now. So in order to prove this proposition, so first you fix x in x, and from the definition of the norm in x prime, you get that the phi of x is less than the norm of phi times the norm of x. But since I'm dealing with such a phi that is less than 1, I obtain this inequality. So in order to achieve our goal, it is sufficient to prove that there exists a specific phi such that the norm of phi is less than 1 and such that phi of x equals the norm of x. And to do this, I can just apply the previous proposition, which gives me the norm of phi node equals x and phi node of x equals norm of x to the square. This is exactly the previous proposition. So now if I want that a specific phi such that the norm of phi is less than 1 and such that the absolute value of phi at x equals norm of x, it is I can just take phi 1 equals 1 divided by norm of x phi node, and this gives the result. So I have a specific phi such that norm of phi is less than 1, so it's phi 1, and phi phi 1 of x equals norm of x. So here this inequality holds, and that's it.